G'day chemistry students. In this video we're going to continue covering dot point 2.2.3 and we're going to be looking at the percentage composition of elements in compounds. So as most calculation videos will be, this is best completed with a periodic table and data sheet in front of you. Now we've already started to do some percentage composition calculations and in that we were looking at components of mixtures, so the percentage of mass of a particular part of a mixture once it was separated. In this particular version of the calculation, what we're looking at is elements that are in compounds. So to determine percentage composition, what we need to know is the molar mass of all of the elemental atoms and the molar mass of the compound itself. And divide those two numbers and multiply that by 100. And what that will tell you is how much of the mass of a particular substance, or what percentage of the mass of a particular substance has come from one of its elements. So as an example here, if I was to do something for NH3 ammonia, what I would need to know is that the molar mass of all of the hydrogen is equal to 3 times its molar mass, which is 1.008 as it says here. We would also need to know the molar mass of all of the nitrogen, and that would be 1 times 14 times, 1 times 14.007, which is the molar mass of nitrogen. Now you'll notice that we multiplied hydrogen by 3 because there are 3 hydrogens in the chemical formula for ammonia, and we multiplied the molar mass of nitrogen by 1 because there's only 1 nitrogen atom. If you were to add up all of those numbers together, you would also get the molar mass of the ammonia as well. So let's say that we were trying to find the percentage composition of hydrogen in ammonia. What we would need is to take the molar mass of all of the hydrogen, which would be 3 times 1.008, and divide it by the molar mass of the compound, which would be the sum of these two parts. And in fact, that's going to be the first question that we're looking at in this video. So let's get to that calculation. All right, so in the first set of questions that I have, or the first question I should say, it reads, as I said before, what is the percentage composition of mass by hydrogen in ammonia? Now, as per what we were looking at in the last slide, what we already know is the molar mass of hydrogen and ammonia. And in particular, what we want to be substituting into our equation is for percentage composition, that it is equal to the molar mass of, and in this case, it will be all of the hydrogen present in the formula for ammonia, so the molar mass of H3, all divided by the molar mass of ammonia itself. Oh, sorry, just messed up that writing a little bit. And H3. And I'm going to multiply all of that by 100 at the end to convert the decimal that we'll get into a percentage. Now, the values that we were working with, as stated before, the molar mass of H3 is equal to 1.008 times 3, which is not plus 3, excuse me, times 3 is 3.024, and the molar mass of ammonia is equal to 14.007 plus what we already wrote up the top, so 3 times 1.008. So all I'm going to do is add my molar mass of nitrogen onto the calculation that I've already started, and that is 17.031 grams per mole. I'm not going to worry too much about any of the units of measurement for this. We are just going to end up with a percentage at the end, but what you'll notice is that we can substitute both of these values into our equation. So I'm going to do that. So the percentage composition of hydrogen in ammonia can be calculated to be 3.024 divided by 17.031 times 100. So let's do that now. So I'm going to make a fraction, 3.024 24, all divided by 17.031. And that's this number here, which isn't the best percentage. So we're going to times by 100 so that we convert from a decimal to a percentage. And I'm going to be reporting my answer to 4 significant figures, so 17.76%, which means that the remaining, if I subtract my answer just then, if we wanted to know the percentage composition of the nitrogen in, or the mass of nitrogen in ammonia, it would be 82.24% as well. So there we go, percentage composition of hydrogen in NH3 is 17.76%. Moving on to the next calculation. This one's a little bit more involved and actually probably a little bit more practical than the first one. I guess the first question was showing you this new step or process, whereas this guy's going to be more of an application to a real world calculation, a reason why we would want to know percentage composition in the first place. So if I had a sample of magnesium oxide, which its formula is MgO, and it weighs 15 grams, the question is what mass is contributed by the oxygen atoms present? So not just the percentage contribution, but the actual physical mass itself. So what was the mass of oxygen that actually reacted with the magnesium to form magnesium oxide, I guess is the more practical version of the question. So to begin with, what we will need to know is the percentage composition of oxygen in magnesium oxide, and from there we can use that percentage to determine what portion of this 15 grams was actually oxygen. So let's get started. So percentage composition is going to be equal to the molar mass of the oxygen, that's the percentage part that we want to get. So the molar mass of oxygen all divided by the molar mass of the magnesium oxide multiplied by 100. Now I'm not going to bother writing up the molar masses like I did up the top here. I'm just going to substitute them straight in. So the molar mass of oxygen is 16. And that's 16 straight, so 16.00 is the number that I'm going to substitute in, which I think is the number that's on your data sheet from memory. I haven't got that one up with me. I'm using another periodic table while I'm recording this, but I'm pretty sure it's 16.00. And the molar mass of the magnesium is somewhere around 24.305. If you have a different version on your periodic table, that's completely fine. Just roll with what you've got. And we're going to add the molar mass of the oxygen as well. So that's just a flat 16. And that is equal to 40.305 grams per mole. We're going to multiply all of that by 100. So let's get that done now. So we have 16 divided by 40.305. I'm going to multiply that number by 100. So the contributing mass of the oxygen is 39 point, and I'm going to give 4 significant figures for this, 70%. Now, if we wanted to know the mass out of our 15 grams, all we would have to do is, first off, I'm going to write mass of oxygen. To calculate that, I take the mass of the magnesium oxide, which is 15.0 grams, and multiply it by my percentage, so 39.70%, which really you could also multiply as a decimal. So you could also, instead of writing this as a percentage, you could multiply it by 0.397 grams, and I'm actually going to do that for the sake of simplicity. So I'm going to take this value and multiply that by 15 rather than taking the number and writing it down as a percentage. You can do it on calculators as well. Maybe that's something that we can look at in class, the 2 different ways of entering into your calculator. But we're going to multiply that proportion by 15, which means that the contributing mass is 5.95 grams. And notice, again, the lowest numbers or significant figures for any of my values that I've used in my calculations is 3, so I've matched that at the bottom as well. And that'll do us for our calculations for percentage composition. Thank you very much, everyone. Now, in the next video, what we're going to be looking at is determining empirical formula. So empirical formulae are the kind of formulae that we write for ionic substances. and I'll define sort of what that is and what that's all about before we get too deep into the calculation part. But until then, have a good one.